The display is slightly different than usual. There's a side. I did the best I can. It's anyway. Nando, can you do a microphone test?
Test. Can you guys hear me at the back?
Yeah.
All right, so let's get started again. So today I was going to talk about scalable deep learning, and I'm still going to say a few brief words about it. And my particular sort of take on it will be, how would you scale deep learning if you didn't have access to all the resources that Google has? However, since this is summer school, I also don't want you to sort of throw you into the my research agenda and so on. But I will take a few steps back and go over Markov random fields and graphical models. How many of you, I think some of you have done machine learning before, how many of you have done Bayesian networks? Okay, very few. Markov random fields? Okay, quite a few of you. So I'm going to go over it still for the other few who haven't seen it before, so I'll go over the introduction. And then I will go over how would you do distributed learning for such models. And that will, again, be sort of new, recent research, which hopefully you find interesting. All right, so there's a very nice YouTube video, and the transcript is also online, by Richard Hamming, titled "You and Your Research," I think. And in part of that video, he goes on about the fact that when he joined Bell Labs, he knew you couldn't get programmers. So he was a new guy doing research. And so he was facing the sort of problem that I think a lot of academics would face now, which is we can't do deep learning unless we have access to all those machines and the grants and so on. Some of us at top universities do have access to that, and the companies have been extremely helpful. However, still a lot of people are marginalized from computing in the world. In some continents more than others. And I think what's brilliant about his take on it was he said, if you're at a disadvantage, that's when you start thinking. And you start wondering, how can I do better with my research? How can I solve this problem? How can I still come up with great things, even though I don't have the resources? And I think for many of you who've been working out there and who initially might have not all the resources that you would like to have, just keep thinking of that necessity is the mother of invention, and that might actually be a really good thing, that will force you to start thinking. Incidentally, at the time, the programmers were mostly women, and that might come as a surprise, given the current poor situation of women in computer science. There's definitely a biased sample here with far more males than females. And I guess that's my 1 minute of political appeal. The parents, teachers out there, please don't tell your students that computer science is only for boys. That's just completely wrong. And it's preventing half of the population from us having access to the talent of half of the population. So I think it's very important that especially teachers and parents realize that computer science is a very useful career, and that if we had more people doing computer science, I think we could do a lot of good things, as you guys don't need any convincing facts. Okay, so yesterday we saw this beautiful lecture by Kwok on CompNet and deep learning. And so I'd like to start by going a bit over that. And in particular here, I'm showing you one of the CompNets by Matthew Sealer and Rob Fergus. Matthew has a company called Clarify. He asked me to tell you that he's hiring. So it's very good. Rob's also very good. He's on Facebook. And he won the last ImageNet competition. And he has this really cool software for visualizing what the deep net is doing throughout the layers. And so you start with your image, you convolve it with one of these filters, and this is, he uses a strike of 2, his filter size is 7 by 7. Initially there are 3 channels for the image, and he uses a total of 96 filters, so that's essentially what this is saying. So 96 of these guys, which that is, for layer 1, each of these images is a filter. So he will use 96 of these guys. And then this here is just essentially the filter responses as you move the filter over the whole image. And then he does what Kwok told us about, which is pooling, to reduce the size to get invariance to minor perturbations and local changes, local transformations. And then sort of keeps repeating this architecture. I believe he also does contrast normalization, and if I'm not wrong, he would be using rectified linear units. So rectified linear units max out. Those seem to be the best things to do these days. Max out and rectified linear units are particularly nice because they're 0 most of the time. And if you haven't seen max out, I strongly recommend you Google that paper. It's a very nice paper. Most units are 0, and they will only be on for a particular type of input. So that's really nice because those networks are context dependent. Some inputs make the units activate. Some inputs don't make the units activate. And I think that's what makes those particular choices of, one of the reasons why those particular choices of phases is nice, in addition to the gradient explanation that Paul gave you yesterday. There is a competition on the Hutton Prize for compressing Wikipedia. And it's essentially a natural language processing task. You're sort of trying to predict the next character. But in fact, you actually only try to, you think of words as actually sequences of 1s and 0s, and you're just trying to predict the next bit. That picture of Kwok, that Kwok draw of, this is how humans see an image, this is how a computer sees an image, it's actually very useful to keep in mind. A computer just sees 1s and 0s in a sequence. And currently the state of the art for that is a technique called PAQ8, which uses PPM, uses many PPM models. Those PPM models are, for those of you who've seen non-parametrics, they're very similar to bit-linear processes, or as Frankfurt and Yewaite call this stochastic nuances. And then there is a one-layer neural network that Matt Mahoney came up with, and that takes, I think he was inspired by Jürgen Schmidhuber to construct it. And that one layer is, I mean, that's a huge network. But what he does is he only chooses a certain, a subset of inputs based on, say, what was the last byte or the last previous 2 bytes and so on. So he has a context-dependent, input-dependent network, which by only being attentive to a few of the inputs, only needs to do computation locally. So the computation goes down a lot by having this sort of context-dependent computation. So Joshua Benches noticed this and he sort of advocates this, and this is something that I think is very important. I started by talking about attention in my first lecture when by showing you those videos of change blindness. And I think in these networks, it's sort of might arise naturally if we think about how to do it. And that might have sort of potential computational improvements. The other thing that is to be noted about these ConvNets, which by now you've looked at it in great detail, is that each filter looks like a nice surface. This is not just a bunch of random pixels. They're actually smooth. And they ought to be smooth because we're learning from lots of data. The data out there in the world is not sort of salt and pepper noise. The data is smooth. And so if we use lots of data, essentially these models are non-parametric, and then they're starting to capture, as a number of parameters just infinitely, is starting to capture essentially the statistics of the data. And that's why these models work, because the set of images that exist in the world is much smaller than the set of all possible images. So if you had, I don't know, 1,000 by 1,000 pixel image that takes 256 values, you would end up having to need 256 to the power 1 million bits to code all possible images. That's actually the number of fibers that goes through the optic nerve, so that's not outrageous. However, I mean, how can we code that number of images of 1,000 by 1,000 pixels if it's such a huge number? In fact, the numbers are huge, that it's bigger than the number of atoms in the universe. Okay, so if your brain had to store all possible images, your brain would have to be bigger than the number of atoms in the universe. So that sort of tells you how much smaller the space of images that we actually encounter in the world actually is. And that's what these filters are capturing, and they're smooth functions. And if you go higher up in the layers, by composition, by this layer compositionality, you start seeing that the filters in layer 3 start looking like objects, or perhaps parts of objects. And these are the images that are in the data set that are closest to these filters. You start seeing dogs, still some other patterns, and so on. So throughout, these will always be these type of smooth functions. There's some nice faces here. Okay, so building on this intuition, and that was for a ConvNet. For a different type of neural net, an autoencoder with a regularizer, a group element regularizer, something that's called reconstructor ICA. I think it's one of Koch's papers with Andrew and Stanford. The filters, again, they have a structure. This is in the first layer. And here's the key, one observation one can make. This representation is extremely redundant. Why is it redundant? Because recall that this image is sort of made out of pixels, and each pixel is one parameter. So you have a surface, and the way we're going to represent that surface is by using spikes. So we're using basically a Dirac representation of an image. That seems to be wasteful. We're representing a surface by using spikes when we know that there's so many other ways of doing smooth interpolation between images. So this brings into question this issue of how we're parameterizing these models the right way. And in particular, if I take a subset of the parameters, and white here means that I removed the parameter, then it's sort of trivial how to interpolate this image to get another image. And there's a huge number of techniques you could use to do that. When we did this work, I used Gaussian processes. That was last year. And my motivation was because I wanted to, and I still have not done this, and I still want to do this, is build a fully non-parametric representation of these. And this is sort of true whether you're doing multi-layer perceptrons and MNIST. It's true whether you're doing convolutional layers on SUPAR and so on. So you always have this redundancy in the parameterizations. And so immediately, sort of the big question for us is how to best exploit this redundancy to reduce the size of the model. Especially because the model, as Koch pointed out, scaling is one of the biggest challenges here. More data, bigger models. If you have lots of parameters, you need to communicate those parameters over a network or across machines, and Alex already told you how slow that can be and how debilitating communication can be. Another reason, if you have less parameters, as you're computing these dot products as you go through the components, you might be able to do these operations faster. So you might be able to have something that's faster with less memory imprint. And that's what you need to do if you want to code a component in a vacuum cleaner, so that the vacuum cleaner can detect, can have vision, or any sort of very cheap consumer electronic device. If we want to, imagine you train the components in your big competing server, and then after training, you might want to sort of do something like this, a test time, just to ensure that you actually can deploy your component on any mobile device. Here's some proof of the pudding. This is for a task of phoneme recognition, as mentioned yesterday. And if we just do this sort of interpolation, in this case with Gaussian processes, you can go down to 20% of the parameters without deterioration in performance. I wouldn't say that the GP is the best way to do this. It's the way we did it because we were coming with a different motivation. But then soon it became clear to us, especially thanks to reviewers for that paper, that there were very good techniques out there to do fast convolutions using low rank representations. And in fact, there's been two papers since then that build on this, one by Rob Burns and Ellington's group, and one by the computer vision folks at Oxford. The one that I mean, they're both sort of doing the same thing. The one of Max Jaderberg, I think it's very nice because he exploits several properties of fast convolutions that people have learned throughout the years. Because a lot has been learned about convolution in the last, since 50 years or so. And so he has a very nice, instead of doing the component the usual way, he has a very nice way of doing it with rank 1 filters and bases. So he does a decomposition of these into these guys. And through doing 3 successive convolutions, he's able to get significant speed ups. Like for this task of detecting digits, he's able to still detect digits, typically with a 5% speed up in the nets. So it's not only less memory, but less parameters to communicate, but also faster. So I recommend you look at this paper. It's very nice. Recently, Max has also been doing a lot of recognition of what the text says, and I think his networks are probably, they're state of the art, even compared against some of the Google nets. All right, so that's ComNet, and that's that work. And I was thinking of going deep into those work, but they sort of involve more advanced concepts. So we're going to take a step back, and we're going to look at other types of deep learning out there. And in particular, we're going to look at Boltzmann machines. They're not the sort of en vogue models, but a lot of the ideas of Boltzmann machines are still permeating through research. Like log bilinear models in language are still extremely useful. They're a type of Boltzmann machine. And they're a very nice alternative to the recurrent nets if you want to do sort of sequence prediction and so on in language. Often we need objective functions that are structured, so you can slap a random field on top of an RVM to just make sure that, say, all your outputs are still related to each other. Alex has done a lot of work in that type of those type of applications with structured labels, structured classification. And so there's many reasons why this work is still interesting. Ruslan Salakutinov in Toronto has also been he's continued working in this area. He's done a lot of good things. So ConvNets are amazing. Tomorrow I'm going to just talk about ConvNets and transfer learning. But the other research that was done in the last 10 years by researchers in this area, I think it's still very relevant, and you ought, I guess, at least at the summer school, you ought to actually be exposed to it. The nice thing is about that work is it will be mathematics to model networks, but not only networks of neurons, but they will allow us to model networks, networks of sensors, networks of people, sensor networks, I don't know how, I guess this is for a drug trafficking network. That's a sensor network. Okay, how do we model this? So since our problems will be networks, it sort of makes sense to model them with networks. And the type of networks that we use to model them, I think it's called Markov random fields in some communities. So we also refer to as the undirected probabilistic graphical models. The directed versions I will not cover, and they're often called Bayesian networks. And there is a way to map between these two representations. And in some cases, one is more amenable than the others, but I'm sort of not going to go into detail in that direction. In these networks, what you're trying to do is you're trying to reason about many variables, say about populations of networks, or trying to reason about populations of users in a social network. And so, for example, imagine this as a social network with 5 people, and think of these as people who are, I don't know, voting yay or nay, thumbs up, thumbs down, or plus, whatever, in the interface, and they're trying to, I don't know, vote on some issue. And then what you might want to do is infer how are they related to each other. What's their sort of, based on their activity, what are the parameters, what are the correlations, for example, between 2 users? And the reason why you would want to ask, so you can think of this age as, in a way, telling you how related users X1 and X2 are. Or if these are firing neurons, what you're trying to find is what is the correlation of firing of these patterns. In a neural network, well, this indeed will be 4 neurons, and you're just basically trying to estimate their parameters, or their synaptic firing rates, the synaptic rates. And in fact, in this network, in the world of neural networks, it's a very old one, and it's known as a Hopfield network. In these models, there's 2 ways to get at these models. One is through a concept called conditional independence. The idea of conditional independence is that the probability of a node given, and the notation S that I'm going to use here means all the variables. So S here will be X1, X2, X4, X3, and X5. And the variable I here is just to indicate just one of these guys. And I might be interested in what's the probability that X1 will say yes, given that everyone else said, I don't know, given that this person said yes, this person said no, this person said no, and this person said yes. It turns out that to be able to answer that query, I only need to know what the neighbors, and here stands for neighbors of node I said. So the probability of X1 given the entire graph is just the probability of X1 given X2 and X3. So that's essentially conditional, the conditional semantics that this graph encodes. So Markov semantics, and hence Markov random fields. There's another way to think of these models, another representation, which is in terms of probabilities over the entire graph. So this is a local formulation of the model. And a big question in AI, the Jitter Pro and statisticians, Stefan Larsen and many others, were able to nail over the last 30 years was, how can you do local computation and ensure that you're globally consistent? And much of the work in probabilistic AI was about that. So in terms of local, so this is sort of a local representation because it only depends on node I and its neighborhood. This, on the other hand, is a global representation. It's known as the Gibbs distribution or the Boltzmann distribution or an exponential model. And it essentially is telling you, it's talking about the energy over all clicks, and a click is essentially a group of fully connected variables. So for example, here the variables x1, x2, and x3, they're fully connected. They're forming a clique, a group. The variables x2 and x4 also form a clique, in this case, a pairwise clique. These four variables don't have a maximal clique because you can still put an edge here and so on. So typically, we can consider all possible cliques, because you could consider all possible edges here. So you would have cliques of size 1, cliques of size 2, pairwise interactions. You would have these triple cliques and fourwise interactions. But in practice, because of computation, we tend to restrict ourselves to just actually mostly pairwise cliques. But keep in mind that for some applications, it might be interesting to look at the higher order cliques. So you essentially are summing over these, and then you specify an energy between these. And the idea of, and this energy basically will be a measure of how compatible two variables are. If you were to have pairwise cliques. Lower energy means higher probability. So you want to find low energy configurations and most probable. How many of you have heard of SAT? SAT, satisfiability. Okay. So if you take a SAT problem, you can reduce it to this, or the other way around. So this is just a way of encoding as well constraints in discrete problems. And from saying that, you should already then immediately realize that finding the max of this probability is empty hard. Likewise, computing Z, and what Z is the sum over the numerator, is what makes this probability sum to 1. So Z is the sum of this E over all possible x's. And since x is a vector here, in this case, if this was binary, there are 2 to the 5 possible configurations to it. And Z, if you have many variables, like a million, you have 2 to the million. You can see that quickly becomes very problematic to get Z because of the. I just said Z. I'm Americanizing quickly. Okay. This is known as the partition function. So I'm going to give you some examples of these type of models in this lecture, and then I will tell you how you could go about estimating the parameters. There is another problem, which is called the inference problem, which is what's the probability of a node given the other nodes? Or what's the probability of x2 given that x5 is on? That inference question I will not address in this lecture. So I won't have time for that. We'll focus on the parameter learning. So here's my first example. This is sort of a typical network, Markov network you would encounter in AI, where you're using symbolic variables, and these might be some variables in this case, because you might want to know, for example, what's the intelligence of someone who is happy, or what's the probability that they will get a job given that they got a letter of recommendation and did well in some test. And so if I use just the first letter to describe this, like I, S, so I can now write this distribution as the probability of C and D, and I, and G, and L, and S, and J, and H given theta, that's just equal to E to the, I'm going to use a parameter theta, CD, times, and I'm going to, let's assume that the variables are binary, so I would use here, actually I'm going to make this a bit simpler. So I'm just going to take that as a matrix, and I'm going to basically multiply C and D. They form a clique here with parameter theta CD. And then I would have to add this next clique, which would have a parameter theta DI G, and that would involve the variables D, I, G, and so on. So I would add all these variables, and then I would have to have here a sum over, essentially, let's call all these variables x. And I would have to have a sum here over x of e to the, essentially the same guy that I have up there. Theta CD CD plus theta D DIG dig, and so on. So that's basically how I would write the model. So writing the model is just a question of looking at the cliques and parameterizing each clique with a parameter, and then you have these, and you write the random variables. So let's look at one particular example, which was sort of quite hot in deep learning 5 or 8 years ago. A binary RDM. So what a binary RDM is a bipartite Boltzmann machine. It's an old model. I think the citations they go back to the 80s. Each variable is binary, as the name implies. We will realize that soon. But imagine that these are sort of black and white pixels. So these axes could be an image of black and white pixels, and this will be essentially whether the neuron is firing or not. These would be the sort of neural representations. And each of these edges here has a parameter. So when you visualize these three edges, what you should do is look at an image with this pixel, and this pixel. And that image is essentially the images of the filters that we've been looking at. So if this was a true image that is long, you would hope that this filter would be like a Gabor filter. It would look like an edge detector. So it would be an image that is gray, and then there'll be a bit of black and a little bit of white. And this is another way that people used to draw this. In this case, these variables are latent, they're hidden, and these variables are observed. And so we shade them to indicate that they're observed, and these are not shaded to indicate that they're hidden. So the model now has two types of variables. So it has a vector of x variables and a vector of h variables. In this case, 4 h's and 3 x's. Each of the x's and h's are binary. So the way we write the energy is a sum over all the d x's. So we assume that in this case d equals 3 and L equal 4. And then we look at the interactions between each bit. So each of these guys would have one particular weight. So this would be the weight W11, this would be W12, and so on. And then you also assign the biases, which are the single node potentials. And you can rewrite this in matrix notation this way, which is kind of what I was doing in the previous slide. Okay, so that's a binary RDM. But you know, sort of black and white images are not the typical images we see. So it's possible to actually put here different types of distributions, t-distributions, Gaussian distributions, and so on. But let me first tell you why this model is actually really cool in learning. Why we should be paying attention to this, even if what we're doing is not deep learning, but some other form of statistics. And that has to do with the power of representation of this model. So typically, as I said, each pixel here is one observed node. And then you have these hidden nodes, H's, so these are the V's. And then essentially, as I'm showing here with the picture, you're loading these filters. And these filters will be the things that tend to occur a lot in the world, the little patches that we see. And the nice thing about this is if you have 5 units, and essentially you're representing, as we see for this image, you can think about it's treating that as noise. I guess because this doesn't occur enough on the data set. This occurs a lot on the data set, so it learns these features. And this quickly gives you an explanation of what's going on in the image. When the computer sees a 1, 0, 1, 0, 0, it knows that it's an image with this edge and this edge. Okay, so that's the mental representation of what's in the image through a distributed code. Now, the nice thing about this distributed code is that I could compose using these guys, by pasting these guys down, I could compose 2 to the 5 possible images. You know, I could go 1, 0, 0, 0, 1, 1, 1, 1. I could start generating lots of images, even without doing convolutions and pooling and all of that stuff. So this is a exponential representation. It's very nice. It's very powerful. It's a very nice representation of world. So you saw you've already seen clustering. Now in clustering, you're taking data and you're putting it into one of k clusters. And even if you use sort of overlapping probabilistic clusters, that is only giving a linear representation of the world. Whereas these models have this very nice encoding of exponential size. As I mentioned, you can make these Gaussian. And if they're Gaussian, you would have, say, a b squared. This starts looking like a Gaussian, basically. This is essentially a parameterization of a Gaussian distribution, and then the parameters of these w's and so on. This is a way of rewriting a Gaussian in terms of this type of network. And just out of interest, it turns out that there is a very nice connection between autoencoders and probabilistic graphical models. So, for example, and a few people have pointed out this connection. I put here one paper that comes from an idea that mostly, I think it was Kevin Swersky who came up with it and led this work. But also Pascal Vincent in the University of Montreal has done a lot of very good work in this area. Building on an estimator called score matching by Alpa Vivarinen, who wrote a beautiful book that I strongly recommend as well on natural image statistics. Also very influential in the sort of development of deep learning. And what Kevin did in particular here was that he realized that if you took this estimator, so score matching is an alternative to maximum likelihood, and if you took that estimator and you applied that estimator to estimating the parameters of a Gaussian RPM, he ended up with an expression that looked like this. So this became the cost function. Halfway through the derivation, the cost function that he had to optimize was this. And what this is essentially what Kwok was telling us about yesterday, where you have several units, V, you have a matrix of parameters, you have an encoder that gives you a prediction of the hidden units H, and then you have a decoder again that gives you something of the same size as before, which is the prediction of the data V. V for visible, H for hidden. So halfway through the derivation, what you get is the energy, so the objective function of an encoder, which is you want to minimize the difference between V hat and V. And then this extra term is a regularizer. So this for Bernoulli variables is just the variance of the hidden units. And then if you're taking a linear combination of the variance, so you're basically looking at the projection, the linear projection from H to V, you're looking at the variance of the reconstructions. So this gives us sort of a natural way to design a probabilistic model. If you're familiar with using RVMs, you design a probabilistic model, and then you apply score matching And voila, you have an autoencoder. You've designed an autoencoder. And then you would apply maximum likelihood to it and so on. So for folks who find it more natural to work with probabilities and constraints and so on, this is a nice way to go about it. Often, it's better to actually think in terms of autoencoders. And Joshua Ben has done beautiful work using intuitions about autoencoding, sort of noise contrast and so on. But it's just nice to know that you can have both representations and that you can sort of map between the two. What I haven't told you though is how to map back, and I don't know how to do that. So that's one of the questions that you can start thinking about. Here's another type of model that's sort of very popular, that used to be very popular in processing papers, which is the sort of grid MRF, where you have some observations of a noisy image, and then the goal is to reconstruct a denoised version of the image. So that's your very popular toy example. Here's a more interesting model that's definitely very used in practice, a conditional random field. So in a conditional random field, you might have, for example, in NLP, they're used everywhere. Let's say in NLP, these variables here might be words like Mrs. Green spoke today in New York, blah, 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 blah. And then you're trying to estimate whether something is a person, other, or a location. So you're trying to see what type of entity you're trying to detect locations, names of people, and so on. So entity recognition. And often to do that, you need long connections, long interactions, because I might be saying that, I know, Obama's the president of the United States, he is awesome, and so you kind of have this, you need to know that, you need to sort of get this co-reference that he refers to Obama and so on. So people formulate these models. Often, the energy is written as a linear combination of thetas times features. So for pairwise model, the feature is just the pairwise interaction, xi times xj. Or the feature will be just a single interaction, xi. But in general, the folks in language, they're very good at coming out with huge numbers of features. All sorts of hacks that they get from linguists and from trying things. And once they have that, then they try to estimate theta, and they put a regularizer on theta. One regularizes on these log linear models, so that basically if a hack is poor, a feature is poor, then that feature sort of is destroyed because the data does not support it. And so these are called log linear models, because if you were to take the log of this, you would have a linear model. And they're also called max-end models because they can be derived as trying to find a distribution that is where you put the least assumption, that is, that has high entropy, but that matches the moments of the data. So you want the data to speak as much as possible, and you want you as the designer to not have too much to say on this, about this distribution. Not surprisingly, that's equivalent to maximum likelihood. Okay, so for the rest now, I will focus on these log linear models where the energy is in this form. Now, one result about this distribution is if we take we have some data, so I'm going to use n as an index of a data. So if we have capital N data cases, then the way I would write the likelihood for that model is would be as P of xn given theta, assuming that the data is IID. So I'm saying capital N observations of xn. So each xn here is the full network. It's the full realization of all the variables. So xn here is a vector of all the components of the network. And so that's the product of n equal 1 to n of 1 over z theta e to the sum of cliques theta clique phi clique of x and c. So now I'm identifying the c variable in the variables in the c clique at time n, shall we say. And then you can take the log of this. And you will get sum of the c, theta c, phi c of x and c minus the log of z theta. And this is a derivation that arises a lot, whether you're doing log linear models for deep learning, log bilinear transformations for natural language prediction, whether you're doing CRFs, whether you're doing, it's just a very, you'll often have to compute this rate. So that's why I'm taking the time to do this. So now if we do dl of theta with respect to an individual parameter q, so the parameters of a particular clique q, then we get n equal 1 to n, and then I have the derivative of a sum of theta, and only one is theta q, so all the derivative of all the other thetas will be 0, so only theta q survives, and I have phi q of xn. I'm being somewhat redundant here with the notation, so I could drop the n. I've already stated here that this is for clique q, so I guess I can do this for some more generality. Minus the derivative of z, of the log of z theta. So now the derivative of the log of a function is the derivative of function divided by the function. So this is 1 over z theta. And now I'm going to take the definition of z theta. So actually, let me do that in 2 steps. So now I need d by d theta q of z. And z, the definition is e to the sum of a c of a theta c phi c of x. And this sum is over both terms. So there'll be, this is inside the sum of n, so there'll be a factor of a. And so this will be equal to sum over n, theta q, phi q xn, minus. Now, if I take the derivative of this, the derivative of each of the ax with respect to x is just a times derivative. So this will just be equal to the sum over x of phi q, because it's with respect to q, of x times e to the sum of a c, theta c, phi c of x divided by z of theta. And then you can see that this is nothing but, again, our distribution. So when you do learning by maximum likelihood, what you're doing is you're comparing the statistics for each clique, the statistics of the data, against the statistics of the model. And that's the key principle to learning. That when you look at the data, you close your eyes, you imagine the data, and if what you imagine is not what you see, then you have to learn. Then you have to update your knowledge. But if what you see is the same, then you don't need to, then you're fine. No matter what machine learning principle you use, you will encounter this. Learning is always about this. It's about contrasting what you imagine with what you see. All principles can be mapped to this. Maximum likelihood does it through the eyes of entropy. But if you take any other estimator, it's always going to boil down to this type of argument. Okay, MLE is data efficient. Go ahead.
When I still theta q in the equation.
Sorry?
There's a theta q.
Oh, the reason why there's a theta q is because I made a typo. Thank you. I apologize. Yeah. Never been good at calculus. Okay, so statistics of the data, statistics of the model. That was almost as bad as Quark's quadratic. Okay, so sometimes you're on the board and you don't see the obvious. Where was I? Oh, I wanted to tell you the maximum likelihood is data efficient, and that would have emerged here. Because in order to compute the gradient, and the idea is you want to use the gradient several times, but you don't need to compute this part in the, every time you do an update of the gradient. You pre-compute this term. And it's linear in the data. So log linear models have this beautiful property. MRFs allow you to do one single pass over the data and just estimate a sufficient statistic. This is known as a feature of a sufficient statistic. So you can actually compute them all. Moreover, you can compute them in a completely distributed fashion. There's no reason why, I mean, you can have machines having data in different parts and then just one single communication of the statistics and adding them up. So it's extremely data efficient. The problem is that now we have to deal with this. Data efficiency came at the trade-off, which is model inefficiency, in the sense that I have to solve this exponentially large, intractable integral. So can we do this? Well, just very quickly, we'll tell you that one of the most popular ways for doing this, it goes back to the 70s to Gillian and Bisak, is something called pseudo-likelihood. The idea of pseudo-likelihood is that instead of maximizing the likelihood, he looks at the probability of each node condition in its neighbors, and he maximizes that alternative estimator. When you compute the derivatives, I haven't done it here, but you end up with something like this, where this is basically the bar here means flipping the mth bit. The details don't matter, but the important thing is that the conditional probabilities, which require that you look at all the data, and for a binary model, this will actually be a logistic model. This will be a sigmoid. This is actually how one way in which the sigmoid arises. And this requires that you keep all the data, so it's very data inefficient for it because you need to do it at each step. Because you break the model into submodels, it's model efficient. We would like to design something that's both data efficient and model efficient. That's the goal. And again, you see you're contrasting statistics. In fact, pseudo-likelihood, the way to think about it is you take a vector and you flip one bit. And you're basically contrasting your data against single flip, all possible one-bit flips of the data. If you try to use bigger groups, you use something called constant likelihood, then you're flipping groups. And then there are stochastic ways for dealing this, in particular stochastic maximum likelihood, and then they're just flipping bits randomly and contrasting. Okay, so here's one approach. An algorithm that is data efficient, model efficient, and requires no communication. There. So here's the idea. We're going to take an MRF, and then for each click, we're going to construct what I call an auxiliary MRF with a particular neighborhood that I'll define soon. So we break the MRF with, say, we go with scissors, cut it into small MRFs, estimate each MRF separately, and then I will make some claims that those separate models, the parameters that you estimate individually, actually give you the global parameter. Local consistency to global consistency. There are some assumptions that must be satisfied. So let's look at an example. If this is your original MRF with parameters theta, what we're going to do is we're going to consider each click, and I'm only going to look at pairwise from now on. If I look at this pairwise click, well, these are, say, two variables here, I need to look at all the variables that are neighbors with the variables involved in that pairwise click. I'm going to redefine a new MRF over this neighborhood with parameters alpha. That's going to be my auxiliary MRF. It's a much smaller MRF. So to give you an idea, for a grid, that MRF would involve these variables. For a cube, it would involve these variables. These are very useful in physics. For a chimera, the kind of model that D-Wave's quantum computer uses, this would be the local. And so for these models, the algorithm will be efficient. For RBM, a fully observed RBM, the model will be inefficient because the neighbor still is basically the whole graph. The vanilla version of the model. Later, I'm going to show you one for which it is actually efficient. So does this work? I mean, this sounds like magic. So the first thing you do is you go and run experiments and you realize, well, the error is kind of vanishing. So this seems to be consistent because I'm getting as good as maximum likelihood. My variance is also going down. So it seems that this estimate is actually pretty good. So it has the same variance as maximum likelihood for practical problems. There is an issue as to how I choose these neighborhoods, which edges to add. And at first, you might realize, well, how do we deal with the boundary? Do we put extra clicks here as a result of marginalizing? So if you have a graph and you integrate out variables, so whenever you have three variables, suppose you have like a tree, a variable A, and then it goes down to B and C. If you integrate A, you form a click between B and C. So that's one of those things you can derive very quickly. So by integrating, by integrating these variables, we're forming these extra clicks, and then the question is, do we add these to the model or not? What my students, Yariv and Misha, who did this work and came up with all the ideas ready, they were realizing, well, that doesn't seem to matter. So that would lead to more theory going over quickly. And that was true for different models. Now, I told you that there's a local representation, there's a global Gibbs representation. These two are actually related. And they're related by something called the Hammersley-Clifford theorem, which basically tells you of the mapping between the Markov property. Something that satisfies the Markov property has this Gibbs distribution. However, it was years later that people actually showed that something more important, which is that it's possible to come up with a particular representation of the potentials that gives you uniqueness. So there is a unique Gibbs distribution for a particular choice of potential. So the existence and uniqueness of this particular representation, which we call the normalized potential, is what will make this work. This is the key thing. So normalized representation with respect to a variable, say a value, let's say the value is 0, basically means that if one of the variables in the click is 0, the energy or the potential will be equal to 0. And that's the existence and uniqueness theorem. There exists one and only one Gibbs potential normalized with respect to 0, corresponding to the Gibbs distribution. And a good reference for this is the book of Kinderman and Snell. So if you Google Kinderman and Snell Markov random fields, you'll get a free copy of it. I think it's the first hit. The PDF is available. And there's also a very nice book by Bremont about Markov chains and Gibbs distributions that also treats this. Now, the key observation is the second observation that allows us to use this result is that the auxiliary MRF is parameterized in this form. It's basically the small MRF. which has all clicks. If I look at the marginal for that neighborhood of the variables that are involved in the small MRF, and the marginal is obtained by integrating out the joint. And I've run out of time to do this algebra, but this is something that you can verify. And if you can't get this result, I'm going to be here. Come to me and I'll derive this with you for a small example. You can show that you can integrate out over all the variables except the variables in AQ, and that this potential that involves the parameter of interest always factors out. So you have the same potential in the marginal that you have in the joint. And because of these guys are parameterized in exactly the same way, that potential must also be the same. That is essentially the key observation. And that's how you prove this proposition. If both of these representations are a normalized representation, then they have the same E and the same Z. Now, moreover, if my E is identifiable, that is, I can recover theta from E one-to-one, then theta is equal to R. And if that is true, then the marginal for theta q will be the same as the model for alpha. And if I use an estimator for the small MRF, like maximum likelihood, which under some regularities is consistent, if my estimator for maximum likelihood of the MRF, the small MRF, is consistent, then the estimator of the global MRF is consistent. End of proof. So the proofs are very simple actually to get. There is this ICML paper that appeared this year. There's a new version of it that I will tell you quickly about the main results it contains. So I'm going to place in 2 minutes and finish this. And this one is on archive. I'm just going to tell you what the results are. We realized that we were by using the whole neighborhood of the click, which somehow came from thinking of blankets of clicks as opposed to blankets of variables. A blanket is something that sort of covers and protects that click. But we realized that the blanket can be a lot smaller. So in particular, we realized that if we choose A, let's suppose this is our click. Whoops, I made a mistake here. If we choose a neighborhood such that it includes the click of interest, Q, but it also includes all the neighbors for a variable J, then it's impossible to find a path through that whole network that will connect outside of A, that will connect the variables J and I. So you're not going to get a problem of double counting. Say, by integrating out, you're not going to generate new edges. So in other words, that keeps I and J separate, and that's what allows us to take it out of the integral. So once again, it will come out of the integral. It will be the same in the marginal as in the joint and as in the auxiliary model. And so once again, everything I said before, all the theorems apply when you use this much smaller neighborhood. And that's actually quite powerful, because that allows you to reduce the size of the models vastly, especially if you have leaf nodes that have no neighbors. You can actually do better, because you can actually define an MRF over the conditional distribution, and because the conditional is nothing but sort of a joint over its marginal. For a variable xj, that's an xk. So think of, this was the first version that I showed you. We weren't sure about these edges. By what I did before in the previous slide was basically saying we only need the neighbors of one guy. So maybe all that we need is this with this extra edge. And now the claim will be that I can actually also work with the conditional, because this will have the potential that I care about as a separate factor in normalized representation, and hence it will be unique. This integrates over one of the variables in the click, so this does not contain the click. And therefore, once again, I do have a representation that allows me to recover the click. And in fact, if you actually consider this being just a single node, what we've done is we've gone back to pseudo likelihood. However, this allows us to use arbitrary size blocks, so what we have now is a distributed concept likelihood method. So in essence, this allows us to now attack an RBM, because if you just look at the conditional nodes, you don't need to consider, you don't need these edges, so the model becomes tractable, the conditional is tractable. And many other models. It allows us to distribute them in a naive way and be able to do the estimation. They will all be consistent. They will all get the same answer as the number of data goes to infinity. However, some will converge at much faster rate. And that's the big question. How efficient will these functions be in practice? We know that if you choose bigger neighborhoods, bigger groups of variables, algorithms do become more efficient. So we proved that. But it's still a big open question to actually sort of go and test these models extensively. So Yariv, who's the leading person behind this, has done this for Gaussian MRFs and tables. And currently, these are open problems that we would like to solve or would like to see someone else solving. Dealing with high parameters, this one should be very easy. Latent variables, this actually turns out to be tricky. Structured learning should be easy. That is, given a set of random variables, how to infer the right network structure. And that's actually very useful. Very useful to do in practice, because you want to sort of learn structure from data. Can we use this for more general statistical models? The many models you're hearing about this week, it would be nice if you start thinking about it. There's a sort of duality between learning and inference. Can we exploit the fact that we have linear and parallel learning to get good inference? And there's a lot of work to be done in terms of theory. And another nice extension, if you like this type of work, of relational learning, would be to take these techniques and extend them to Markov logic. And that's pretty much sort of the end of the sort of researchy part of my lecture. Tomorrow I'm going to come back to ConvNets, and I'm going to go over the details of ConvNets for language, how would you implement a convolutional network for language, and how to use them to do sentiment prediction, and also how to use them to do transfer. Like if you have a label, if you know the sentiment of a review, how do you use a ConvNet to get the sentiment of an entity that the review mentions? All right, thank you.
Sorry, but I wanted to. Yeah, it's
Yes, signal?
Second?
Yes, signal?
Yep, let's get my tape. Okay, so today we're going to switch gears a little bit. So in the past 3 lectures, we basically looked at how we can actually go and distribute models over several machines. And that in combination also with Moose Talk should have given you a bit of an idea of how you can take a model, break it down into individual components, and then distribute those components over a large set of computers, and then therefore solve it in the distributed fashion. So that's a really useful thing. However, what it doesn't do is it actually doesn't tell you necessarily how you can deal with very, very large models and actually make them fit into memory. Right. So today, we're going to go and look at 2 different versions of how to accomplish this task. And we may or may not actually be able to finish the last bit, namely the cuckoo hashes, simply because, well, I guess Zico actually has a couple of announcements to make, and so overall we might run out of time a little bit. So this is something that actually came out of the talk that Muthu Krishna gave in Pune at a workshop maybe about 5-6 years ago, and actually Muthu is the next speaker up, assuming that his flight and everything works out fine. So here's what is actually still a very common approach to dealing with text. I mean, yes, you can have a deep network, and deep convolutional networking. You can do a lot more sophisticated things. But this is still a model that's going very strong, and I just want to use it as a motivation, namely vector space models for documents. In other words, I just count how many times a particular token occurs, and I turn this into a vector, and then I can do efficient inference. Okay. So that gives me, nice linear functions, for instance. So I have vectors w.x plus maybe some constant. And these models are in extremely widespread use. So for instance, for spam filtering, internet advertising, ranking, retrieval, you would be surprised how widespread the use of those models is. Now, the catch is that those models will work really well as long as we don't have too much data. Too many parameters. Because at least if I store things inefficiently as a double, I need about 8 bytes per floating point number. So I'll end up with about 8 gigabytes of memory for 1 billion floating point numbers. If I have a sparse data structure where I basically have to store at least the hash of the word ID, I might end up paying something like 12 bytes. If I manage to compress the floating point a little bit, okay, maybe we are back to 8 bytes. So in other words, 8 to 16 gigabytes is not an unreasonable amount of memory to spend on 1 billion parameters. Now, what if I have more? Right? This is not so uncommon. For instance, if I actually have a large user base with maybe 1 billion users, and each of those users maybe needs on his own at least a couple of thousand parameters, then you're talking about 1 trillion parameters. So how can I actually deal with such gigantic models and still do efficient inference? Maybe solve an L1 penalized problem, which then gives me back a model that ultimately can fit into a small amount of memory. And so basically, how can I make the model small enough if I can't upgrade the memory of my computer? So let's look at a slight motivation for this, and this is essentially an example of a hierarchical model. Personalized spam filtering. So let's say somebody sends you an email, and this email goes to a lot of users. So then, well, those users might actually annotate this email in interesting ways. So, I mean, this is the ideal user you want. Well, she gets the email, and she annotates it as spam, and, well, that's great, but not all users do that. I mean, after all, Nigerian spammers also got to live, right? Some users just have no idea what that button does. And I guess we've all done enough tech support of that form. Well, spammers have email accounts too. They even have stolen credit cards and so on. So there's a fair amount of mislabeling there. And may I ask, when was the last time you labeled an email as spam? 1 week ago? 1 month ago? This year? Okay, so that's the problem, right? In many cases, it turns out, fortunately, you can actually infer from the user's behavior, whether an email is possibly spam or not. So, as a piece of advice in your own interest, if you want to have high-quality spam filtering, do label. And I'll show you a little bit of a picture of how labeling actually helps you directly. So here's an easy way how you could solve the problem, right? Each of those users gets his own classifier, and we decide to spam filter on their own classifier. What could possibly go wrong if I did this? Any suggestions? Why is this a terrible idea? Yep.
Most users will get bad classifiers.
Most of the users will get bad classifiers. Why would they get bad classifiers?
Only 1 out of 5 people did the right thing.
Well, because only one of them did the right thing. Well, that's true. A much more serious problem is that most users don't label a lot of emails. So the training set for each user would be minuscule. I mean, it would be maybe 10, 20 emails. And, well, each user getting his own classifier maybe isn't too bad. So, for instance, I'm terrible with administrative emails. And I might occasionally actually skip and ignore them or maybe label them as spam. On the other hand, that's exactly why I have a really great admin who makes sure that I don't forget all the administrative emails that I really need to take care of. And some people might feel inadequate and actually might want to reply to some body part enhancement or otherwise stimulating things, right? So, in other words, everybody's idea of what spam is slightly different. So, in other words, the spam classifier that works for me might be a terrible thing for you. On top of that, well, if I have a spammer, right, wouldn't it be nice if I could make the spammer believe that his own spam gets through, but nowhere else? Right? So, but the big challenge is really that each user gets his own subset of emails, and there isn't a lot, and especially, well, she's not going to get anything. So, that doesn't work. So the solution to that is to try to have a bit of the best of both worlds by having what's called hierarchical model. In this hierarchical model, what you do is you basically have a global classifier which essentially tries to deal with the aggregate consensus of what is considered spam by most humans, and then also model the slight deviation that each individual has relative to the global classifier. Who has heard about the kill file before? Or basically how to deal with trolls in the old days on the internet? Okay. I guess everybody knows what the troll is, right?
Yeah.
Okay. So if a troll signs up in a forum, well, he will go and start, writing stupid stuff, and people get upset, and they start, a flame war, and then at some point, the moderator of the forum decides, well, okay, it's time to kick this guy out. So he closes down his account, and guess what happens? The troll comes back under a new ID, and he keeps on doing this. Okay. So in other words, constraining things by restricting the accounts is only of limited use for a really persistent troll. But what's much more effective is if the troll doesn't get any replies, then he'll just be very frustrated and go away and go somewhere else. And so what people at some point realized is that you can actually do this, namely in such a way that only the troll gets to see his own posts and nobody else sees them. And so this way, well, the troll realizes that nobody likes his very insightful and deep comments, and he goes away and draws somewhere else. Okay. Effectively, what we're building with this is a machine-learned version of such a kill. So basically, what we're going to do is we're going to build a system where the spammer sees his own spam arriving on his own accounts and nowhere else. And we'll do this by having personalization for each user separately and a global consensus. So this way, the spammer still sees that, all sorts of other spam gets rejected. So for instance, a diploma mill will still see the 419 scam being rejected, but, well, diploma's not. So here's how you can do this. And let me quickly show you the pictures. Apologies for the animations not being so pretty, but Keynote between versions decided to destroy all my slides, so these are PDF backups. So what you basically do is you have a consensus classifier, right? This is basically some file-based. This is, for instance, our valid first representation of the document. We have some common parameter. Then for each user, we have his own parameter, WU. And the aggregate score of spamminess, in this case, and you can do a lot of other things than just spam, is composed by the sum of the general consensus score and the user-specific spamminess score. And now, what you can do with a slight degree of manipulation, we saw a little bit about feature spaces and so on already, you can basically write the features of the document, or whatever else the user looks at, product with one direct sum plus the identity of the user. So in other words, what I've done is I've pasted all the user vectors, user parameters plus the common parameter, into one gigantic vector, and all the features also in one gigantic vector. Since this is linear and this is linear, and I just go and match up coefficients, this is just fine. This is just a mathematical nicety, right? There's no real difference between those two models. This is just much nicer to write out. However, it turns out that this gives us a clue how to deal with this model efficiently. Right? Because now what we've done is we've turned the multitask problem into a linear classification problem in a ridiculously much larger space. So how much larger? Well, let's say we have 1 million different tokens that I could receive. And so that's 10 to the 6. And let's say I have 1 billion users, so that's 10 to the 9. So then that means we are operating now in a 10 to the 6 plus 9 dimensional space, right? That's pretty big. Now, by the way, this is if we were to look at the kernel that is associated with that, we would have to take the inner product between this and for a different document X prime and a different user U prime, we would basically get this kernel here, right? Because whenever we have the 1 here, we just get k of x and x prime, the inner product between bar of x and bar of x prime. However, when the users also match, I get an additional increment here. So it's basically twice the inner product when the users match, and otherwise just simply the inner product. Okay, this is, as it turns out, a fairly well understood and old idea. So basically, Pontel and Micheli proposed this about a decade ago, and Heldon wrote this beautiful paper about embarrassingly simple multitask learning with the help of maybe a 10-line Perl script. Basically, what he did is he explicitly constructed this representation, which is kind of cool if the number of tasks is like 10, right? But we have, tens, hundreds of millions of tasks, namely each user is his own task. So while you can still solve this efficiently, on tiny probes with, a dozen tasks, for many numbers of tasks, you need to use something slightly different because, well, even in a benign case, well, we are talking about 40 to maybe 100 terabytes of possible parameter space. So you cannot possibly hope to solve this. At least not in the next few decades, because, well, you know, even if you look at Moore's law, you might have to wait many, many years before machines will have that much memory. Okay. So, how do we solve this? So, one thing that I guess you will actually see in Mutu's lecture is the count-min sketch, but in the context of what we're doing here, let's just see. Okay, actually, let me. Okay, so keep this picture in mind when you see Mutu's lecture, but let me just give you a brief idea of what we're doing. We're basically taking a vector, and we are mapping it into another vector that is lower dimensional, namely sufficiently low dimensional that everything works. And for each coordinate that we have, we just pick a random hashed coordinate there, we'll multiply it with some value. Let me give you an example of how this really happens in practice. So let's say you get some email, possibly spam, right? And a simple thing that you could do, but don't worry, we won't need a dictionary later on, is, well, we take each word, we perform a lookup in a dictionary which maps the word like mention, or the word mention composed with the task Barney, so mention underscore Barney, into a word ID. So this is something that's very commonly done to tokenize. And so we get this, you know, very large vector. I mean, that's basically this 40 terabytes dimensional space. And then what I'm going to do is I'm going to take a hash function. So this hash function takes this token ID and then maps it into a lower dimensional space. But actually what I'm going to do is I'm going to, well, this slide is old. I'm going to actually multiply this with a sign of +1 or -1. It turns out we're not the first ones to have come up with this. This is something that Chen, Farrah, Colton, and a few others actually thought about in the context of the count sketch. And yeah, Moses Charlie Farrah. So he actually was a co-winner of the Candelabri Prize. So now here's what you actually would do. If you think about it, you really don't need this dictionary, right? Because this dictionary, all you do is you just have to do a lookup. Then you turn the word into a number, and then you turn the number into another number by using the hash function. Instead of that, you just feed the string, the identifier, directly into the hash function, and you get something that sits there. And on top of that, what I'm also going to do is I'm going to multiply the contribution by 1 or -1. So I'm going to refer this as a Rademacher hash, you know, one-bit hash. And by the way, one-bit hashes are very easily obtained from generic hash functions. Just pick any bit that you want, let's say bit number 42, and then check whether it's 1 or -1. Do not take the value of the hash function, divide it by its maximum value, and then check whether it's greater or less than 1/2. I know this sounds like a joke, but I actually just recently had to go through some code where somebody had done this. Okay. So now, once we have this feature vector, all I do is I now take a linear classifier on this compressed vector, and I happily go my way. Sounds like magic, right? I mean, this sounds like a really crazy incantation that goes and takes a very high dimensional vector, compresses it down to something smaller, and then, you know, with suitable +/-1 multiplications, just ignore the rest. Who knows what the birthday paradox is? Okay, good. So basically, what it means as a corollary for this room here is that I can, with very high probability, make a bet that there will be at least 2 people who have the same birthday. Okay. Now, joking aside, what it really means is that if I have, for instance, a hash function or just any other random mapping, which maps into numbers between 1 and n, that if I have more than order square root n many such insertions, the probability that I will actually have a collision is going to be very high. And the threshold is going to be at order square root number of L bits. So remember, we had, you know, this, you know, possibly 10 to the 12, 10 to the 13 dimensional space. And we now map it into something that fits into memory. So 10 to the 9 is pretty much going to be our limit. you can see that actually things can possibly go quite badly wrong. So chances of collision are fairly high. It turns out that even though those chances are fairly high, they are usually not disastrous. The reason why they're not so harmful is because I have, as one can show, and I'll get to that in a moment, you can show that basically the orthogonality of vectors, basically orthogonal, is preserved with very, very high probability. And basically, I can essentially turn very high dimensional linear algebra with very high probability linear algebra that in this hash space is still highly accurate. So there's a lot more theory behind this, and there's basically, basically a lot of sketching literature, a lot of random projections literature that you can use to give much deeper analysis. But I'm just going to convey the intuition of what happens. Okay. So, as I've already mentioned, you don't need a dictionary, which is actually a big deal, because in most practical cases, the dictionary will take more memory than the actual parameter vector. So this is good news, because now you have, I challenge you to actually implement a dictionary for this that will use less than 12 bytes per word. I don't think you can do it easily. So, but the point is, if I don't need a dictionary, I don't even have to worry about the memory footprint. It also means that if a new word comes along at any given time, I can still deal with it efficiently. I have a predefined amount of memory. It's a finite memory guarantee. So this is actually really useful. On top of that, in contrast to locality-sensitive hashing, so this is basically some of those other techniques, which basically take a vector and project it with a dense matrix onto a low-dimensional space. I don't get the dense vector out of it. If the vector was sparse before, it'll stay sparse. So let's have a look at it in a little bit more detail. So what's really happening is I take this original vector, that's the email that user Barney receives. It's like very, very sparse. And it gets multiplied with a maximally sparse matrix. This matrix has exactly one non-zero entry per column, but it may have more than one non-zero entry per row. Well, actually, it has to, since the number of rows is less than the number of columns. And the entries are going to be plus or minus 1. They're essentially random. The reason why I'm using hash function rather than a random number generator is that with the hash function, I don't need to store the result of the hash, because each time I feed in the same argument, I get the same thing back. So hint, if you have an algorithm that requires a lot of random numbers that you need to look up over and over and over again, don't actually do this, but instead use hash functions instead. So this way, you will never need to actually have that data structure for the lookup. And what you're basically trading off is memory and data structure versus computation. Because of course you need to invoke the hash functions again, but then quite often processes are much faster than memory lookups, so you are actually going to win, especially on very high multi-core systems. Because they share the memory bandwidth, but the CPUs can do all of the other things locally. Now, let's check a few things. So let's check what happens if I take an inner product, I hash up each of those vectors, and okay, so here's what happens. I basically have sum over all bins which have a collision. So wi sigma of I, so that stays there, and basically hash of I equals j. That's basically the jth bin here. Likewise, for the second vector, I also need to check whether that bin is the same, and now I have to sum over all the bins. So, okay, so this is basically what happens if I take an original vector, I hash it down, take in the product there. Now, if I use a Rademacher hash, so basically where the probability of I being 1 or minus 1, likewise I prime being 1 or minus 1, that probability is just delta I prime. So, in other words, only if I and I prime are the same, then those values will always be the same, otherwise they will be uncorrelated. In this case, taking the expectation over this quantity here immediately shows me that the inner product is preserved in expectation. So what I've basically done is I've turned my inner product into a random variable where the expectation of that random variable is the original inner product. And by concentration of measure, and after all, you know, we are summing over maybe a billion dimensions, this is not too bad. Okay. So a couple of nice things are, so if I have orthogonality before, then in the smaller dimensional space, things are still approximately orthogonal, and you can immediately check that basically just by using, you know, Höfting. It's very, very straightforward, because what you basically have is have a random variable where each of the entries is a bounded value, a bounded range, and you know the expectation of that random variable, namely it's going to be exactly what you wanted before, and then you just apply standard tail bounds. So this is very, very straightforward. What it means is that whenever I have, you know, initially a direct sum in Hilbert space, then by using hashing, I actually get the sum in this hashed space. This is a very useful property. So for many tensorial and other representations, when I would have tensor products before, I can actually turn them into much more useful representations otherwise. The good thing is that the hash inner product is unbiased, the variance is small, and there's a lot more, much more sophisticated detailed analysis by Kumar, Shalosh, and Dasgupta from 2010, and then a follow-up paper by Clarkson and Woodruff. And interestingly, okay, they cite us, Clarkson and Woodruff cites them, but they give tighter bounds yet again for the hash count. So this is essentially what you can do. All of this would be in vain if it didn't actually work, but it does work. So this is a small data set. This is 20 million emails, about 400,000 users, and this was still at Yahoo, and obviously I cannot tell you what the actual baselines are for spam filtering, so we just normalized that to 1. So here's what we did. We first took the unpersonalized spam filter, and we hashed it up into anything between 2 to the 18 and 2 to the 26 dimensions. So 2 to the 20, that's a million. So what you can see is that you can't really see much. Namely, the performance is pretty much the same throughout, and basically, you know, starting from 4 million dimensions, you don't really see anything. Which is actually kind of nice, because the vocabulary is clearly larger than 1,000. So the birthday paradox didn't hurt us too much. So if you haven't seen anything about birthday paradoxes and similar things yet, there's a fantastic book by Mitzenmacher and Upfall. I think it's called Probability in Computing. So it's a fabulous book. Get that, read it. It's nice reading, and it'll help you a lot. And it's extremely well written. Okay, now, okay, so what we saw is that, well, you can't see anything there, right? So this blue curve pretty much, you know, 1 million dimensions matches everything. Now, for the red curve, we couldn't actually get the correct baseline. Remember, this black line is the correct baseline where we really look at all the dimensions, and you can do that in the unpersonalized case. But for the personalized case, the number of dimensions would be too large. So all we can do is we can just look at how it performs. And what you can see is that as you add the number of dimensions, well, things tend to get a little bit better still. But you know, going up here by a factor of 4 in terms of the dimensionality doesn't really help you very much. But what you can overall see is you get about 1/3 reduction error. By the way, really bad idea, and I've seen people try it more than once, so do not waste your time on that. Playing with the number of bits is a bad way of regularizing your model. It's an extremely bad way of regularizing your model. Don't try it. Also, playing with the hash functions is an extremely bad way of improving things. Don't do it. Unfortunately, I've seen people waste weeks on this futile task, so just don't. It's really a waste of your time. It's much better to actually start thinking about more interesting representations of the function class. Okay. So the interesting thing, however, is that, well, there are all those users that are really lazy, right? And for them, well, we don't really have many emails labeled. So what you could actually, or would want to do, is you might want to see whether even for those users that don't really label very much, and that's the majority of the users, I mean, remember that's a lot, whether they still benefit. And so it turns out that they actually do. So what you can see here is a graph of the same error rates as what I showed you before, but now stratified by the number of annotations that each user gives. And so you might actually ask, how do I know for a user that didn't label anything, whether it's correct? Well, you can just take a user who labeled at least one email and remove that label, or you can use other indirect signals to infer whether something is correct or not. Okay. So that basically shows you that you can actually very efficiently compress function space representations and make things fit. Okay, let me show you another application. And given that Mutu isn't here yet, I think it's perfectly okay if Zico makes the announcement about competitions and everything at 11 o'clock, so I'll be basically using up the time until 11, and we'll just wait until Mutu shows up. Okay, so here's the issue. So spammers at some point realized that, let's say Viagra, if they put that into an email, the spam filter will figure it out and then reject the email. Okay, so what they did is they used all sorts of creative and interesting ways of misspelling that word without really, trying to circumvent the spam filter. It's kind of a tug of war, because if you respell it very different, then, the intended recipient will not be able to read it anymore. And the intended recipient are usually people who are maybe not people with a PhD, right? So you can't really use a very large hamming distance. On the other hand, if you stay very close, then it's easy for a spam filter to, detect it. But the problem is you now need to actually generate all those wildcards. And here's the general idea. You basically want to use the spelling and all the misspellings, and you actually want to cover this much, much larger space of possible string variations. And by the way, this is not just used for spam filtering, but you can use the same thing also for bioinformatics. So, for instance, if I wanted to not sell Viagra, but misspell Carnegie in all sorts of interesting ways, these would be some of them. But what I can basically do is I can replace individual characters by wildcards, and I can do that for any one position. And now I can basically check whether I have a match between one string with a wildcard in, let's say, position 3, and another string also with a wildcard in position 3. So this way, I get around the issue of having a combinatorial explosion in terms of the alphabet size. So, for instance, if you think about it, okay, so here's at position 5, basically this would match not just card 3GIE, but it would match any other character that I could put in here. So this, to some extent, reduces the complexity in terms of having to count how many different mismatches I have, from exponential in the dictionary size to something that's now only polynomial in the number of wildcards. So that's rather much more beneficial. But I still now need to actually, count all those fragments, and instead of counting them, I'm actually going to use the hash count. So let's take a DNA sequence. I guess everybody knows the movie that goes with it. If not, you should watch it. But let's just also, of course, a sequence of base pairs. What I'm going to do is I'm going to turn this into all sorts of substrings. This is actually something that people do. It's something called a spectrum kernel, where people have actually analyzed this. And so this would be basically, 3 mares, 4 mares, 5 mares, and so on. Right? So I can do that. And then I can go and also look at all the approximate matches here, maybe for the 6 nodes. And this again leads to a combinatorial explosion. Again, I can actually go and insert that into the hash. So if you look at it, doing things brute force here would require 45 terms, but if I just use hashing, then this is actually quite trivially done. So there are a whole bunch of papers which look at amazingly sophisticated data structures for storing all those approximate matches and so on, but if you use hashing, you can just throw out the data structure and be happy with it. So that's why I'm advocating it. I'm going to skip over the matrix compression. I'm just going to, okay, great, Mutu is here. I'm just quickly going to show you what happens when you want to, okay, just a moment, when you don't actually want to have mismatches and collisions. And so this is actually some very, very new work. It's not entirely published yet. But basically, this works around the issue of, well, what if I don't actually like collisions? And it comes with a big caveat, namely, what if I don't like collisions, but actually my final model, if I apply sparsity, fits into memory. So it'll take me about 5 minutes to explain this. And this came out of an idea. Basically, at some point, somebody asked me when I was talking about the hash kernel, well, suppose I actually want to have L1 sparsity and the final model is small enough. Can you solve the problem exactly then? We first tried actually using hash kernels directly, and it did not work very well because basically there were too many uncertainties in parameter recovery on real data. But there's an efficient way of avoiding this. So I need to show you another data structure that's actually really nice, and it's actually also on GitHub. So Dave Anderson has a very nice implementation of this. So who has heard about the cuckoo hash before? Wow, some people actually have heard about it. So that's great. So for everybody else, the idea was proposed by Papp and Rodler in 2001, and they almost got everything right except for one minor detail, and I'll get to that. And basically, here's what happens. If I have arbitrary keys, and I want to store them in such a way that lookup for key values is constant time, then one way of achieving this is, well, I just create an array, and what I now do is I compute the hash of the key. Let's say, for instance, mention underscore Barney, and we go somewhere. Let's say at position A. And if that location is empty, everything is good, and I just write the value for mention underscore Barney in there. If that location is already taken, let's say, for instance, here, then what happens is I compute a second hash and try another location. Okay, good. Well, nothing particularly interesting happens if that location is free. Then I just insert it in that second location, and everything's good. Now, what if both locations are taken? What happens then is I actually go and evict the thing that's in the second location. Goes here. So B has to go. It gets evicted, kicked out of the nest, hence the name cuckoo hash. Then it finds its own new location. Now, if that location was taken as well, that element would get kicked out, and you would just keep on doing this until at some point everybody finds its space. So what you can clearly see is an insertion may trigger off a very, very lengthy chain. But it turns out that if the array is not too full, and there's some very nice theoretical analysis for this, you can get away with short insertion chains. So what you're exploiting here is the fact that while insertion may be more than constant time, the lookup afterwards of something that's already in that list is constant time, because there can only be two possible locations where a particular key could be found, either the first or the second location. The problem with this approach, however, is that you need to actually store the key in that location, And unless you know that it's there, well, you won't be able to actually find out whether what you have. And the problem with this is twofold. First of all, that key can actually be very long. And if it's very long, then, well, I end up having to use a variable length data structure and all sorts of other things. So I need this secondary list that I index into, or do something else that's very expensive. And the key trick that Dave Anderson came up with is to basically just store a small signature in that location, and then use XOR to decide what hash location 1 or hash location 2 are. So here's really what happens. So I basically store a small signature of the key in that location. And then I compute the hash of the signature and XOR the first hash with this other hash. So this gives me hash 2. But of course, since I have XOR, all I have to do is just XOR again, I get the original hash back. So I can flip-flop between those two locations without really ever having to look up the original X again. Of course, there's a catch. The catch to it is that, well, I've now reduced a little bit the range of different locations that I could have. So H1 and H2 are not quite as independent of each other anymore as they should be. And right now, this is an open theoretical question to prove under which conditions this is still good enough to really have a very short terminating chain in practice. Well, I have a short terminating chain. However, in practice, it works beautifully. So we skipped that little ugliness and actually used this. By the way, to deal with poor fill rate, you actually have several slots per location here, but I'm not going to discuss that in more detail. The nice thing is that as soon as you've sort of kind of filled your cuckoo hash, basically think of it as a sparse vector, additional requests at a particular location are now constant time. So you can do all sorts of interesting sparse linear algebra much more efficiently than with any other sparse vector structure, data structure. And then one or two other things, you basically use clever things like prefetching, because you don't quite know at which of the two locations it is, so you basically queue up the request and then check whether the first one's there or the other one. So this way, your linear algebra library does not stall while you're actually pulling things from memory. And the nice thing is that if I have a distributed algorithm, and this was one of the motivations, I can have my own sparse data structure on each machine separately, and when I merge it, it's still fine to actually reconcile them because I have exactly those signatures. And again, I need to be careful about the birthday paradox and a few other details. But basically, this means that I can very efficiently have local sparse data structures that are easily synchronizable in, basically time in linear time of the number of elements in the data structure. And it also works amazingly well in practice. So what you basically see here, these are the most boring pictures that you would be seeing. Namely, we compared, liblinear, which basically does expensive pre-processing, to what we do with cuckoo hashing, and the accuracies are the same. And furthermore, the actual runtimes are the same, except that we don't need any pre-processing. It doesn't sound like a big deal here, but if you actually have many machines and you would actually have to synchronize the pre-processing, well, that would be a big issue. We probably didn't argue the case well enough because Katie didn't like it, but I think it's still quite useful. So let me conclude with this. It's much more efficient than, for instance, the unordered STL map. So it's about twice as memory efficient, a data structure. And this is kind of funny because, well, this is basically solving the problem exactly, but up here is actually a ridiculously high key space, except that you can tokenize and do a few other crazy things. But basically, what you can see is the cuckoo hash, which is solving the, in this case, gene classification problem exactly, outperforms the hash kernels, and it gives you exactly the data structure that you want, which is actually useful if you're a biologist because you actually care about motifs and so on. And I think this is my last slide now. and I just want to leave you with this. So if you're interested in clever data structures, there's a lot more that can be done rather than just using, well, for instance, just parsing the algebra library. Overall, I believe there's a lot of really interesting things that are currently happening at the intersection between, well, data structures, systems research, machine learning, and also statistical models. And I think it's only going to get more exciting in the future. And this is my last lecture, so I want to thank you for the attention. And I'll hand over to Zico for a whole bunch of good news about computer resources and competitions and so on. Okay. Thank you.
Question, I think you won't record this. So.
Yes. Oh, yeah. Can you stop recording, please?
Yeah, stop. And let's also kill. So maybe we just tell everyone, hey, we'll be back in 5 minutes. Or
yes.
15 minutes.
Well, we'll mute the camera.
Okay.
Otherwise, mute the microphone.
I have some stuff on.
Because unfortunately, Hangouts is so interestingly set up that. Yeah, this is live stream. Okay, so while we're setting up, this boundary line is necessary because that's the slot factor of the video. Okay. So while we're setting up, let me announce to Krishna. So we only have him here today, but well, we sure will make him work very hard. 3 hours of lectures. He just flew in this morning, so just be kind with him. So he's been at pretty much every major company that there is, I think, right now. Looks at Microsoft, or are you still? But yeah, at some point he was at AT&T, and at some point also at Google. He's done a lot of amazing work in direct computer science, and well, to my great disappointment, he has not changed his hairstyle today.
Last week?
Well, at least from last time I saw you. So the lights will come on in a moment, but the projectors and the system seems to insist on wanting to take its sweet time before it allows me to switch the lights on. Sorry about that. Should only be another minute.
Can you do a sound check?
Yeah, sound check's about the next thing. We actually need to.
You want to try speaking?
I can move it aside. Okay. Okay. Great. Okay, so yeah, you have an hour or whatever. Yeah. Okay, so
Hey guys. Thank you.
let's.
Thanks for having me here. I think the last time I came to Pittsburgh in CMU, I think Lilo took a picture of me, and she wanted to use it to convince graduate students to come to the school here. I think that didn't work out well for her. I'm very happy to be here. I think Alex called me and said I owe him, so that's why I'm here. I don't know why I owe him. And also, I understand there's a summer school in machine learning, and I'm not a machine learning person. I'm more of an algorithms person. And that's actually always difficult. Anyone who does cooking thinks they do algorithms. Right? Anybody who does anything in computer science think they do algorithms. And so my brand of algorithms research is about what you can prove about these methods, and what can you design as human. I don't know if you have traveled, when you travel, you have people sitting next to you in an airplane and they ask you, what do you do? I don't know what you answer. You don't want to answer machine learning. They think that you drive, you get the cars to drive with themselves and rockets to launch with themselves. And something similar with computer science, right? You don't want to tell people you do computer science. They immediately tell you that they have a problem with the Windows operating system or something. They want you to fix the Mac. It's something similar with algorithms. If you go to a computer science meeting, you don't want to tell people you do algorithms. Instead, everybody thinks they do algorithms. So with that, I'll give an example of a puzzle, which is an algorithms puzzle. So there's a long history of puzzles. They're mainly in mathematics. People love to solve puzzles in mathematics. So when you say puzzles, almost always they're going to be mathematical puzzles. So I like to collect more puzzles which are more computer science or algorithm. So here is one of those puzzles. You have an n-sized array, and each element here is an integer. Let's say in the range 1 to n or 1 to n squared. And this is your input. Your output is to sort this array. Okay. This is another one of those magical words. I used to teach algorithms to guide the students, even undergrads. Nearly any question I would tell my students, I'll pose a problem, there's a graph, you have to find the shortest path, you have to do a traveling salesperson tour, and I'd ask them, so how long do you think it's going to take? And almost always the students would say n log n. Okay? But it's a bound that's burned into our memory. Right? Computer scientists, this is a bound burned into memory. So we're going to sort this array of size n, but we're not sorting arbitrary numbers using comparisons, we're sorting integers, which means you can do bucket sorting, radix sorting, and so on. So we want it to work in linear time. Not n log n, which is what you need if you do comparison sorting. Here we don't know how to do comparisons, you can do other machine operations, so it's going to do linear time. And more or less, as soon as you hear this, you know how the algorithm should work, right? You're going to read each element, an integer in the range 1 through n, so you declare another array of size n. And then every time you see a number, so you see number I, you go to the index I in the other array and mark it or something. Okay? So that you can sort, then you can go to the other auxiliary array of size n, and you can pull out the numbers you just sorted out. But that uses order n extra space. Right? You have to declare another array of size n and use that as a temporary space to do the sorting. Okay? That uses extra space. So I want to solve this problem using very little extra space. In other words, besides this array where the numbers are stored, you don't have maybe a constant number of words. Okay? So what does word mean? You got to be a little bit more precise. It's something like log n bits. So why do we need log n bit words? If you're storing n in an array of size n, you need to at least index into the array, so your address is going to be like log n bits. So each word is log n bits long, and if this array stores numbers in the range 1 to n, so the array is also log n bits long. So each word, you have seen the random access machine model works on words. So we operate on words of memory, and each word is assumed to be log n bits long. So you have a few extra words, maybe 1, 10, 1, 2, 3, 10 space, and you're going to sort this n elements. Okay. The question is, how would you do this? So just to back up, if there are n numbers in arbitrary range, you look n log n. If there are n numbers in the range 1 through n, you can do bucket sorting or radix sorting. And that will take linear time, but use linear extra space, linear order n extra space. And here the problem is to do that, but with order 1 extra space. And the question is, how would you do it? Okay. So by the way, I don't like this kind of format where I stand here and people are above me out there. Okay. And I like a room where everybody's on the same level. It's an educated hierarchy always. I like this layout, it's a little bit more level. So I'm going to assume that we're all on the same level so you can talk to me. Okay. The idea is to try to solve this problem. And think of it as an interview question. So if it's an interview question, if Alex is interviewing for Google, he might ask you to solve this problem. Okay. So a couple of things you need to do is that you don't want to wait for a long time for you to get the inspiration for the problem, right? You start speaking. You tell Alex the first idea you have how to solve the problem, and then you observe his body language, and you realize that you're going the wrong direction, and then you pretend all along that you were just meant to go in the wrong direction, and you change the direction a little bit. So it's a negotiation. Answering a question in an interview is a negotiation. It's a bargaining process. And Alex would give up a little bit, and then you say linked list, and you say, oh, all right, okay, so no linked list. So this is the way you do it. So you got to think about how to solve this problem, and it's not the idea of getting the final solution, it's the idea of getting intermediate answers and sort of working through the final solution. So if you can think about it, it'll be interesting. By the way, this problem was given to me. The reason I wanted to start with this puzzle is because it was actually given to me by a machine learning person. It was given to me by Mary R. Mori. And he was working with finite state machines, and he needed to do some transitions out of a state. He had a large amount of states. He could label the states, and he needed to somehow index and find the right states. I don't remember the context for it. I mean, I don't remember the final application, but that's where the problem arose. And so, in order to solve this problem, unfortunately, you can't just go with the math you know from high school and college, right? You know discrete math, you know how to sort, calculus. You can't use those techniques. You need to know algorithms research, right? You need to know that you can do merge sort in n log n time without using any extra space. So you can do to do quick sort. Well, do you need extra space? So how do you do sorting without using a lot of extra space? And you can do, in fact, you can do n log n time algorithm for sorting without using extra space. And you want to use those as sort of primitives or black boxes to get this work to do the work. So, and also the other thing is that you don't almost always want to, in research, you have a goal. This was something that my advisor Joel Spencer taught me. He said that you write down the theorem you want to prove. No, and that's really very useful, right? You want to say that there exists an algorithm that uses order 1 extra space and does sorting in any time. So you write down the theorem, and it's a question mark. The theorem is not true yet. You haven't proved it. It could be false. Then you say, well, what can I change? Can I do it in n log n time with no extra memory? Can I do it in n log n time with no extra memory? What's nice about algorithms research is that there are only few functions that we really care about. Okay? There are very few functions that arise naturally. Right? So suddenly you can do this in n log n time if you just use existing merge sort or existing sorting algorithms which don't use the extra space. So while you can't get this theorem, you can clearly get a theorem that says n log n time with constant extra space. So you can meet this requirement quite easily using known algorithms. What you don't know is how to meet this requirement at the same time. And you know that regular bucket sorting would need order n time, but it will use order n space. So those are your operating points. And you're trying to figure out any intermediate result that will be useful. You might be able to solve the problem in linear time, but use order n, square root of n space. Or square root of log n, square root of log n space, and then try to get it down to constant space. So that's another way to think about it. So
I have a question.
yeah.
Can the numbers repeat?
Yeah, the numbers will repeat, yes. Yeah.
That is harder.
In this order?
Yeah.
Well, if they don't repeat, then I can write down item 1 through n as a loop. So there's got to be some repeats for it to be not. So imagine the numbers in the range 1 through n and the n numbers. There's got to be some repeat for it to be non-trivial. And if you're solving the problem of numbers in the range, say 1 through 2n, and there are no repeats, if you assume there are no repeats, I'm good with it. If it helps, you can assume that there are no repeats, but there are numbers in the range slightly larger than n, 2. So here's another technique that we do in algorithms, which is useful. Just to say, well, I don't know how to solve this entire problem, but let's see if we can solve part of the problem. So the part of the problem would be to take a small portion of the array. So let's say, let me write down this methods. 1, use some sort of an in-place merge sort. It's called in-place because it does not use any extra memory. And that takes n log n time and order n space. You can do order n time something like square root of n space by radix sorting. And if you want to see how that works, think of each number as a log n bits in the range 1 through n. So think of it as 2 numbers of log n over 2 bits each, a tuple. So each number would be a pair of numbers in the range 1 through square root of n. So each of the log n bit numbers can be thought of as the number A1, A, and B, and each of them will be in the range square root of n. So you can sort numbers based on this part of the tuple, and then sort it based on another part of the tuple. So each time you sort n numbers, the numbers are only in the range 1 through n square root of n. So you can bucket them, chain them, and so on. So you could get this down in, let's say, something like square root of n space. Okay. So these are some of the operating points. Okay, there's some details, but these are the operating points. And you're trying to get even fewer word usage. So what we're going to do is we're going to take some small amount of numbers here, and we're going to sort them using one of the methods we know already. Okay? Let's say we take n over log n of these guys. Okay. And then we sort them using this method. Okay. Well, this takes the number of numbers multiplied by log n, so this whole thing will take only linear time, and it would use order 1 space, and it would sort this part of the array. Okay. So that should give you some power, because, well, still working with the linear time and constant extra space, you sort the part of the array using the known method. It's a little bit wasteful method. It's more than linear time method, but you're applying it on a smaller piece of the array, so it's faster. So it still works within your constraints of running time. But then you got this rest of n minus n over log n left to go, and this is a large piece of the array. Okay. Even n over 2 is a large piece of the array. It's still asymptotically the same as n. So you haven't really made a big chunk of progress. So progress on a big chunk of the problem. So then here's an observation. Just look at these n over log n numbers, and once they're sorted, look at them as bits. Then if you look at the highest order bit, there are a bunch of numbers start with 0, and a bunch of others start with 1, right? So if you can keep track of how many of them start with 0 and how many of them start with 1, which means something like log n bits to keep track of, then you don't need the top bit. You can strip off the top bit of every number. If you strip off the top bit of every number here, you got something like n over log n bits saved. Okay. So you save this. You can save n over log n bits by removing the top bit of every number. Because all you need to keep track of how many zeros and how many are ones. It's in a sorted order, and once you keep track of that, you know how to retrieve the original set. And in the process, you use log n bits to keep track of how many zeros are there and how many ones are there. So if you look at it, this is beautiful, because asymptotically, you've figured out how to free up something like n over log n bits. And that's it. That's pretty much solves the problem for you. Once you freed up this many bits, we have a solution which will do the arithmetic sorting with something that's square root of n word solution. Now you can apply this method. Okay. And that's all you have to do. Okay. So just to summarize, what you do is you take a small portion, you sort it using an expensive algorithm, but the small piece is such that the expensive algorithm will still be within the linear time of the original array. And once you sorted it, you realize that the items are in a sorted order, so all you had to figure out, you can remove the top bit of everybody. If you keep track of how many zeros and how many ones are there, you can retrieve the original collection. But when you do that, you freed up something like linear bits n over log n bits, and that's enough for you to do the rest of the part. And that's really it. Now you can push this idea a lot. You can, you have worked through some of the details of exactly how arithmetic sorting would work. It has got to be stable, yada yada yada. But, it's, I mean, researchers know that when you do research, you're struggling to find this. You're constantly thinking about the simplest version of the problem to solve and the simplest idea that'll work. And then research gets to become detailed. And I think of that pretty much like eating fried chicken. There's only one way to eat fried chicken. It's a beautiful thing to eat, but the only way to eat it is to go to a room, close the door, and eat it inside the room, so that nobody sees how messy it is. That's the only way to eat fried chicken. That's the same thing with doing detailed development. Right? Once you have this main idea, you write down all the details. N over log n is not quite n, it's not square root of n. It's got to be stable in the second part. We can work through that. So what I did. There's a long history in computer science of minimizing the various resources we use while solving problems. The most natural resource people use is time. Right? They want to make the algorithm as fast as possible. And there's all this polynomial time notion from that. And nearly about the same time in the 60s when this developed this theory of running time, there was also a theory of space that developed this. If you want to use as little space as possible, you may not even care about the running time if you can solve a problem with very little footprint of space. Then how would you solve these problems? There's an entire theory developed as well, and they didn't quite get the same attention that the time results got. Right? A bunch of reasons, primarily that even now people don't think of space or storage as a constraint. And there are examples of kind of techniques we can use to squeeze a space on a problem. You heard, and I sort of walked in a few minutes in Talaga's talk when he talked about cuckoo hashing, which is another way to squeeze in some of the spacing hashing. So there are a bunch of nice techniques for squeezing the space use. And what I'm going to do in the first lecture today, half an hour, is sort of give you a few application areas where we deal with a lot of data. And I want you to sort of work with me as I talk through which of these applications actually need you to think of them as large data set problems, or big data problems. And I'm going to sort of work myself into a world where we want to solve this problem using as little space as possible, as little memory as possible, and it's going to be really draconian space, right? We're going to be able to not just use log n bits with in constant word. We're going to use one word or log n bits, in some cases even fewer, and we're going to solve these problems, and it's going to have a lot of applications. Okay? And the second hour of lecture in the afternoon, I'm going to talk about some of the scale structures. You've already heard about some of them, so I'll try to be as efficient as I can be. And the third part, I'll talk about sort of the new areas, techniques, and problems. So I'll try to connect it to learning least squares regression, matrix approximation, and so on. So it's not. I have a feeling that these lectures are not going to be as deep as others have seen on the schedule. Okay, and I've never seen, I've never seen machine learning people of some of the category I see in the list give a talk without using heavy mathematics. We're not going to have that here. I don't know. Hopefully, the idea is to try to do something a little bit fun. Okay. So for those who want to think about more puzzles, let me tell you a homework puzzle to think about. Now we have an array of size n, and these also comprise numbers, but they're not integers, so you have to only use comparisons to sort them. You can't use hashing and array to sort them. You can't think of them as bits. Okay. So you use comparisons, and the problem you're trying to solve is find the smallest index such that AI has a copy somewhere. So you're trying to find the smallest index such that if you look at the number in that location, it is found somewhere else in the array or the down array. Okay. So again, the idea is not to figure out whether it's a copy or not to find out what is the element that's a copy. What's returning is this in the index of the array, where the element is found that has a copy also. Okay, this is key to the problem. And we have to use order 1 extra space. I think this was a problem from Informatics Olympiad, or some sort of Olympiad equivalent for informatics. I think this was a problem from there. So you're trying to solve this problem, finding the smallest index that is a copy elsewhere, if any. And you're allowed to use only very little extra space. Okay, why is that relevant? If you can use a lot of extra space, you can think of each number in this array. Say look at the ith number, and you can think of it as a tuple I comma ai. Okay, and now you sort them. Okay. And once you sort them based on the first index followed by this element in the array, then you will, in one pass, figure out which element has a copy, and you'll in fact find the smallest index that has a copy as well. Okay. So if you just think of each element ai as I comma ai and sort the whole tuple, you'll be able to solve the problem immediately. And but that would require 2 in space or n extra space. And we don't allow that. We want to solve the problem with small space or n space. And again, if it's a question of finding any duplicate, that's an interesting problem that has a history in solution. The problem instead is to find the index that has the smallest index, so there's a copy. There's a very trickily posed problem. Okay. At this moment, I don't know I don't have a final solution for this problem. So, for example, I have a solution which takes n log squared n and solves this problem in order on space. And I don't have any proof that that's the best one can do. And I have a solution which takes n log n time and solves the problem, but it will destroy parts of the array. I'll end up using overwriting certain elements so that at the end of the problem, solve the problem, I would not be able to maintain a copy of all the elements that I started out. Which is not a very interesting thing in some cases. Okay, so it's a problem. You can figure out whether you want to prove an upper bound or a lower bound, but that's where we are. So n log squared n if I don't destroy the array, and n log n if I'm allowed to destroy it. And I'll really think about it. By the way, in the database community, there's been a lot of focus on big data, like as in other communities, machine learning included. Okay. And the question has always been, what is big data, right? Did anybody have a conversation about this in the summer school? No, all right. Okay. So the person with the red shirt, what do you think? What should we call? What should be big data? This is beautiful. What should be big data? So the point that there is a panel discussion in the database community means that this is a pretty tricky question. Right? The database community is thought about a conference called VLDB, which is a very large database. And then there is a conference called XLDB. Okay? It can only be done by retail industry. Something called XLDB clearly means extra large databases. So somewhere there is a place where it becomes big data, which is different from, assuming that XVLDB is gone for maybe 20, 30 years, the database community is necessarily somewhat confused by this idea that there is a notion of big data. So, in what way do you think big data is different from just large amount of data? So different very large data or extra large data. How many of you are from CMU students? Very few, and most of us are guests from outside Carnegie Mellon. Okay, so all right, the rule in Pittsburgh is that we have to answer questions to the talk. Okay, that's a rule. Okay. So we got to make up some answers. What do you think, sir? I'm looking at you. In what way do you think big data is different from just very large data or stuff?
Speed.
Sorry?
Speed.
Speed. Yeah. Okay. Good. So there is the VCs define big data in terms of these 3 V's or something: velocity, so speed is one of them. That's data that arrives at very high speed, and that's one aspect of big data. I don't know what the 3 V's are. Volume, velocity, and variety. Is that right? Okay. Every once in a while, when I need entertainment, I go to the Starbucks on Sand Hill Road in Palo Alto and spend the entire day there. If you haven't been there, it's a real cultural experience. The Starbucks the whole day consists of people there are HR people doing recruiting and firing. There are people doing startup company who are meeting the VC. There are interviews for 14-year-old programmers. The entire VC industry runs out of the Starbucks on Sharon Heights. It's a nice experience to hang out for a day and observe this. Incidentally, I was there that one day, and there was a man walking around who didn't seem to be part of the VC community, based on how he was dressed. And so he would walk up to people. He walked up to me and said, "Hello, I'm God." He said, "Would you like to donate to my cause?" And I thought it was funny. But then I realized that he spent 6 hours in the Starbucks, and I was also there for 6 hours. But, he kept talking to people and introducing himself as God. And it got more and more interesting. As the evening came along, he was on the phone. He would call somebody and say, "Hello, I'm God." "No, I'm really God." He says, "Do you remember you promised me this money?" You can see the other person on the other end being confused about it. And then he says, "Well, no, I'm God. I really own everything you have. I own your car and your house, etc. I just need you to give me the money." This person was really serious about being God and kept the conversation up. I thought that was pretty remarkable. And so big data in the VC world is this velocity, volume, variety, and I spent a lot of time thinking about this. Most computer scientists in database communities now are not impressed by volume. Okay. We dealt with a lot of volume data before. I'll go to some examples. We're not really dealing with variety. You don't do many things with a variety of data. There's got structure, or doesn't have structure, audio, video, yada yada yada. We know how to think about them. We have a language for talking about it. We know what the open problems are in each area. We're not. Velocity, there's the area of streaming, which I'm going to talk about that deals with velocity. And we have incremental algorithms which work very fast. So I don't know. So as a computer scientist, I don't know how to understand the 3 V's. I understand as an industry person that it gives you a nice structure, nice focus. I don't know how to understand the computer science person. So one of the things I realized, for me, the definition that works is that big data doesn't have much to do with size, right? Imagine if the government kept track of every star in the universe system and did a whole bunch of machine learning on all of the stars. We wouldn't really be very concerned about it. We wouldn't be very excited about it until they find something cool, like another planet or something, like where humans or living organisms exist. So the idea of this being a large amount of stars, galaxies, a large amount of gas molecules. Imagine there is the NSA has a social security number for every atom in the universe and manages it. Doesn't really excite me. Right? It doesn't excite more people. On the other hand, if they happen to be humans, if they keep record of every social security number of every person there and try to follow them, that becomes more interesting. So the big data, really whoever coined the phrase, I'm sure, did realize that big data is really interesting because it has to do with the data of people. It's got to do with individuals. It's got to do with the big part of it is like the big brother part of it, the big pharma part of it. So there is whenever with data, there's going to be, the big data for me has to incorporate privacy and. So one of the things I'll talk about towards the end of the 3-hour lecture is sort of how to use some of the algorithms for new definitions of privacy as well. So that's sort of what I'm going to do. I'm going to give you some examples of data sources. So let's start with the first simple data source. All the research papers were done by some author. Okay. I'll take Alex as an example, but I think in the history there are people who have done a few more papers than Alex. Okay. So now who can guess what's sort of the most prolific author in the history of humanity? So there are people who have done some very, very prolific things, right? So imagine you. Or somebody who's written so much that we are in awe of this person, right? And take all the papers they wrote and think of that. Is that a large data set for us? Okay. I don't know. These papers like a 200 or 300 kilobyte, let's say 1 megabyte in the worst case. Doesn't mean that vision people have some pictures or something. Then let's say this person wrote 3,000 papers. That's a lot. I don't know many people who have written. I think in the modern history, maybe Kurdish may have written 1,500 papers. So we put the numbers together, this will be less than 3 gig or something. So this is not something that's going to impress us in terms of data sizes, not velocity. Velocity is not very good. So anything like a time series. So every 5 minutes, the number of observation of temperature, pressure, yada yada yada, number of people who land in Pittsburgh, number of airplanes that leave, number of people who come to the country, the number of. So anything that's a measure such that every 5 minutes you measure something. So I remember there was a researcher in AT&T that many of you know, he had a small space algorithm for a problem, and he said this would be very useful for AT&T because we want to apply it to measurement of what happens every 5 minutes in the network. If you think about it, if you measure something every 5 minutes, there are sort of 20 units in an hour, 24 hours per day, 360 days a year, say 10 years. This is about 100 by 4, this is about 1,000 by 3. let's make this 5. So it's 5 times 10 raised to the power 5 or something. Okay. That's the amount of observations you have. Each observation is a few hundred bytes. You're still talking about something less than a gigabyte. You don't need a lot of small space algorithms to deal with this kind of stuff. This is anything that you can declare a main memory in most of the laptops. So a lot of time series observations don't tend to be large enough size for us to think of significantly new algorithms that have to minimize space. The time series may be useful for people to sort of think about what kind of questions would you ask. Supposing I kept track of a number of people who arrived at each of the airports in this country every few minutes. Then, and let's say we had this for the last 100 years, last 50 years. Then you could ask what kind of questions are interesting. You might want to ask, well, how many people landed in Phoenix in March of 1983? So it's a kind of a range query, and you can answer such queries. You can ask, is there any time period where the number of people who arrived in LAX is more larger than the number of people that are at JFK? So these are very natural questions that you can ask if you have such a data set. And most of them tend to be questions like point queries, like what happened on a given day, given moment, what happened in a range, in some time interval, or you can compare between two of these moments between LAX and JFK. And the natural questions you can ask. And then you can get more general and ask questions like, is there any trend? Is there a weekday, weekend trend? Is there a summer, winter trend? Or can you predict from there how many people will come in the next week, next month? These are all natural questions to ask. So it's good to keep that in mind because I'm going to, for the most part, talk about really simple problems like answering these point queries and range queries. But once you do that, you can build up from there to look at things like comparisons, trends, and then machine learning classifications. So that's the way to think about it. So let's look at all the things that, say, Google would collect, or Facebook, or there's an interesting company called Flurry, which is a mobile analytics company. So it's a piece of code that is in a lot of apps in cell phones, so that the app developers can keep track of the events happening in the app. So it could be you install an app, you download an app, you use an app, register the app, how often do you use it, do you do in-app purchases, do you click on ads in the app, and so on. So it's an analytics company. Okay, there are a lot of analytics companies in the web. This is an analytics company for mobile, and it keeps track of, it's used for analyzing the performance of apps. So you can imagine a company like, so imagine that Google keeps track of all the people who come to Google, pose a query, and it keeps track of some information about the geolocation, whatever, what kind of browser they use, and what query they asked, and what kind of results were presented, and did they click on it or not, and assuming that they keep track of all of this. You could have something similar with Facebook. You can keep track of the number of people who access the Facebook app, number of posts, number of walls, number of friends to look at, and so you can keep track of all the events that happen. Same with YouTube. And you can look at this and say, well, is this a very large data set? Does it have the velocity? I would argue that the companies like this phase may be about 10, let's say 50 billion transactions a day worldwide. And each transaction entails, say, 100,000 bytes. Okay, so you may want to keep track of some information about the user, so the transactions, the outcome, the 50,000 bytes. Okay, and that's the kind of range in which these companies would be, like 50 billion transactions. Each of them is about 1,000 bytes. So maybe like a few tens of terabytes of data. It's going to look like a large amount of data. But what is more interesting here is that when you look at this data set, you don't tend to go and ask the question, well, what did Mutsu do in Facebook in 2012? That's another point where that's interesting. You don't tend to ask what's the number of all posts done by people who come from zip code 9.006. Those kind of questions appear to be a little bit less interesting in this case, right? The questions that are more interesting are things like, what model would I fit? What can I learn about how will users behave, and how will they respond to ads or respond to recommendations and news? And that's where sort of more machine learning kind of paths seem to be more interesting on the data. I want to contrast it briefly with, say, cell phone companies. So cell phone companies can keep track of all the calls you make. So who called whom, what time, how long did the call last, and what kind of network elements they attached, and you can sort of look at this collection of these factors. Okay. And this is a large data set. It's a pretty reasonable data set. Maybe not not quite in the range of this, but some orders of magnitude smaller. But now, the kind of analysis that you do with this is a little different, right? You don't tend to really ask questions like, this cell phone, who are they going to call next? Because cell phone companies are not in the business of trying to recommend telephone numbers for you to call others. That's not the business. So they don't. So they're most likely to ask questions about, will the traffic be so large that I need to buy new routers or new switches, new connections? Am I making good use of my network? Am I routing them the right way? And how much money do I spend rerouting for each other? And those kind of questions. And finally, there are ISPs, or internet service providers, that keep track of all the packets. So these are IP packets. So they have some source IP address, destination IP address, and the port numbers they tell you, and the payload, the content. Okay. So this will get to a situation where these are orders of magnitude even bigger than this. They operate about, I don't know, 100 gigabits per second routers in the backbone, because they're aggregating all of the internet traffic, all of this. So each packet there, so each packet gets handled in something like, well, let's see, I try to do some calculations with, let's even take a 40 gigabits per second link, and that's this many bytes, and this many bytes. And let's assume that each packet is about 100 bytes, which is reasonable. Some packets are much smaller, the TCP, the Atlas packets, you do not care about them. Okay. And so that makes it something, and for each of the packets, you might store, each IP address is 32 bits, maybe even 64 bits, but it's about 4 bytes, 8 bytes, 10 bytes or so, you might want to store 10 bytes. Okay. And if you do that, then you have something like half a gig of transactions that you're going to keep track of per second. This per second. So if you think about that, it means that each packet, this is a number of packets for which you're writing that logs. Each packet gets handled in something like, so the amount of storage that you keep is proportional to the number of packets in such a way that in each second, when you handle a packet, you're handling them in something like a few nanoseconds. And therefore, you're going to write data at the rate at which these packets are being handled. So you're going to write data at the rate of nanosecond access speed. Now you have a problem of the velocity and volume and so on, because while the memory is very cheap, most of us can go and buy 100 gig in any local store for $100, less than $100. Okay? Those things don't operate at nanosecond speed. So if you want to write logs as you see the packets in the IP network, you have to have storage systems that operate at that speed, and then memory gets very, very expensive. Then you have a situation where the volume is large, and the speed is large, and you want to use as little space as possible, because the space you're using is a nanosecond memory access, response time memory, and that's very expensive to get. Okay. So this gives us a space. So if you look at the, I want to make sure I have one more. So what's interesting about this application is that you've seen the competition that's been set up for you and you've seen the last few years. These companies, while they store a reasonable chunk of data, it is not as big as the IP traffic data. Okay. So even these big internet companies that look at application level information don't deal with the data of the size and velocity or volume of what an internet service company does. But the difference between these two applications is that these companies typically tend to ask simple questions. They tend to ask questions like, who are the people spending a large amount of bytes, and how do they control their traffic? If a link went down, how many people, which routers will be affected, which customers will be affected, and so on. So they tend to ask that kind of network level questions. Well, companies in this space, while they deal with slightly less sort of volume of data and speed of data, they tend to ask more complicated questions about users' behavior, what summarizes the state of the mind of the user, will they click on something or not. So they're willing to store the data into multiple machines, use multiple machines to solve the problems. Okay. So these are the sort of two really thrilling application scenarios for large data set analysis. Right? So these companies are able to maintain data about individuals, a reasonably large amount of data, have infrastructure through a lot of machines and computing time as a problem, and they want to solve very sophisticated exercise. And these companies tend to have very, very large volume of data, very large amount of data, very fast. They don't tend to do a lot of sophisticated analysis, and they don't throw a lot of machines and infrastructure at the problem because it's not the main business. The main business is to make sure they route properly and make sure they do fast routing times and make sure that the network doesn't go down in security. So these are the two spaces of problems that we're going to focus on. Here it's going to be the case that explicitly we want algorithms that will use very small amount of memory because the rate at which you want to access memory is so high that the memory will be very expensive to operate. The question is, here, do we need algorithms which use small space, or small representation? And it turns out that if you use multiple machines, then one of the big bottlenecks is going to be communication. So we still need, we tend to focus on small space algorithms for this application because we want to be communication efficient. So in other words, the classical theory of computer science of sort of minimizing the running time, as I said, we sort of extended to look at algorithms which minimize space used. And now we realize that we want to extend that to algorithms which use small amount of communication. Okay. So we're going to basically focus on these kind of algorithms from here on. We want to take problems from simplest problems like graph problems to lookup problems and range problems. We want to design data structures that use very little space, and we're going to use them in a communication efficient way. Okay. And we're going to see how far we can push a theory of algorithms. That's what we're going to do for the next 2 hours after lunch. But I'm going to leave you with one conceptual question to think about. Okay? So I said that there's been a classical theory of databases for a long time, and I said that what's interesting about the big data is that the data has to do with individuals, and that makes it an interesting problem. Okay? So it also brings up an interesting aspect of databases as well. So think of a database as the database of, forgive me, Alex, I'm going to use Google example. But I know it's an easy company to pick on. Okay? So think of Google as a database that answers questions. Okay? So I want to think of the database as a strategic agent. Okay? Imagine if you're a database and in some like a science fiction, you want to grow. Okay? You want to grow and gobble things, and you're a database, right? You grow by having more data. How are you going to grow by having more data? Okay? Well, people respond to you directly. They ask you questions, you give them answers. If you get them the great answers, they're not going to ask you more questions. So if you really wanted to grow, you're trying to constantly think about how do I give answers in such a way that they'll ask me more questions and will grow. Okay. So it's an interesting aspect of database for me that you want to develop a theory of databases right now in which the questions are being asked by strategic agents, and they have some utility. And you, as a database, you have an utility, and your utility is to grow. If you can develop a nice game theory around this, I think that'll be a very interesting world. So in other words, you want to develop a game theory where the database gives an answer that is not optimized for all the utility of the users, and it's not optimized for its own utility. You have to develop some theory of an answer to the query is no longer sort of semantically correct answer. It's an answer that maximizes some utility function for the combination of the individuals and the database. you can develop that theory, I think there's a lot of that could be found something fun to do. Anyway, I'm going to stop there. It's 12 o'clock. When I come back, we'll do some sketches. We'll do applications to privacy and other areas that we'll think about.
If anyone wants to talk about setting up the cluster on your own group, come chat with me now, or we can chat after lunch. So it was like I saw this. Very, very